And then we've got some interesting things to talk about for the immediate future over our own region, and then maybe longer term, if we get a chance to talk about it, across North America broadly. So it's been an interesting week. I'll just remind you that through the day Monday, why did I do that again? Through the day Monday, we had our 5th straight day in November of a high temperature of 70 degrees or higher. It was 73 both on Sunday and on Monday. I think 70 on the first of those 5 days and 71 on the middle 2. So that's never happened before. We had 2 other instances of 3 consecutive November days with a high temperature higher than or at 70 degrees. That was in 2008 and then again in 2015. But 5 in a row is, I think I put it in the newspaper, it's sort of the equivalent of breaking Joe DiMaggio's hitting streak from 56 to 85 games or something like that. It's a giant leap to a whole nother category. And I should mention, we came close on the 2 days before that streak began. We were 68 and 69 respectively. So we had probably 7 straight days over 68 degrees Fahrenheit this November, and that's probably never happened, although that was a little bit harder to trace easily. And so I don't have that exact information. But that was an outstanding prolonged warm spell for this time of year, and it wasn't just here. It was widely across the northern plains, so really a wild beginning to November weather-wise. And then, of course, it was followed up on Tuesday night by passage of a pretty intense precipitation band along a cold front. I'll show you some evidence of what was going on with that. That was influenced by the near proximity, I believe, of Ada, because 2 of the last 2 days of our heat streak were dew points of 58 and 59 in November, which is simply unbelievable. And you don't get those dew points unless you're somehow flexing the tropics poleward, and you were with Ada to the east and a deep trough well to the west, and we were in the south-southwesterly flow that was dragging those incredibly high dew points to our high latitude location. In fact, Greg, the more I thought about this, about the connection between the hurricane, tropical storm, and the heat period, was one of the reasons we got to 70 on a couple of those days was because the temperature never got below about 58 overnight. Yeah, right. So you only have 12 degrees of warming, and if you have clear skies, that you can do that in November with no snow on the ground. So absent the tropical storm and the dew points being maybe 40 or 45, we don't get to 70 on those days, even though we have nice days. So it's totally related to that, even just from that perspective. So I think if we were to look back at the historical periods of consecutive days over 70 in November, it might well be some influence of tropical storms. And the individual 70-degree days probably are not, but the ones that come in bunches probably have something to do with it. And the unusual lateness and potency of this, of Ada, may have put us over the edge on those 2 or 3 of those days in the 5. So just amazing how it all kind of works together. So here's the satellite picture for right now, for the last 6 or so hours, and we still are talking about Ada. There it is, off the Carolina coast. Yesterday, this whole cloud mass and the precipitation associated with it was a little bit more linear along the entire eastern seaboard from Gulf of Maine all the way maybe down to the Carolinas. Today, the northern part of that looks a little more ragged, and really all that survives in the deepest clouds is the actual remnants of Ada. And as it goes out over the Gulf Stream again, it's seemingly getting energized in terms of at least the depth of the clouds. I don't know about the circulation, so maybe we can take a look at that in a minute or two. Broadly, the tropics look rather active for November. Couple of convective complexes just north of the northern countries of South America, and then a whole bunch of disturbances out in the eastern Pacific as well, south of Mexico. And over the continental United States, we had a frontal passage last night. We're sitting outside around 8 o'clock, 9 o'clock. It was 51 degrees or maybe 48. This morning, ice all over the place. A little bit of rain came through, and you'll see on the 850 millibar chart, there was a decent but very local region of temperature contrast that came through and put us in the colder side now, where we still reside. And then the central United States is clear pretty much across all of that region. You get the sense from this cloud streak here across Arizona, New Mexico, and then into Oklahoma, that there's a subtropical jet streak, and we'll see when we go to 300 millibars, indeed that's the case, and exactly in that place. And then you can see obliquely, we'll look a little more directly in a minute, open cellular convection over the Pacific Northwest, the northwestern part of the or northeastern Pacific, and that testifies to really cold air at upper levels. We'll see that in a minute. Greg?
You know, NHC is picking up on that.
This one here?
Yeah, they have that up to Cat 2 by tomorrow.
Oh, is that right? And is that iota, or is that?
I think that would be iota.
Okay. And we have 30 already, is that correct? Did I hear? Who said that? Somebody said that when they walked in. 30 named storms this year, and that's of course a record. The old record was 28, I think. And so we're already into record territory, and we've got another potential disturbance brewing over northern South America. I don't think this has happened before with my machine, not so frequently anyway. Okay, so yeah, even more to come in the tropics. I was complaining to Pete beforehand in 452 and 751, but especially in 452 where we're doing a weather discussion every day. I keep getting my weather discussions hijacked by the tropics because we have to talk about them. And I wish that we didn't because we have other things going on in the mid-latitudes. But all joking aside, what a year. It just keeps on coming. Okay, let's take a look at the radar across the continental U.S. And really there's a sprinkle of rain here in the northeast. And that's tied to that cloud mass, tied to the weak cyclone that went past us just yesterday, the cold front yesterday evening, or maybe the day before. And then this is just some sort of interference. There's not really anything going on over the southeast in terms of precipitation. But this is the little bit of eta that can be picked up by the Hatteras radar at just about the 200 nautical mile limit. So it's the backside of it. It's too bad we can't get a better resolution of that. And then there's precipitation coming in the Pacific Northwest. Some of it looks organized at first, and then up here in the Puget Sound, you see it's just a collection of open cellular convection cells. And that's we talked about this in class this week, actually, talking about precip distribution around fronts. The Cycles project described post-frontal rain bands. We don't get those here in the central United States because the only reason you get them out in the Pacific Northwest is because the stability is so low when it gets cold aloft, and you get these convective elements that sometimes organize into lines in the shear. Not apparently today. And next, wait a minute. I thought I had a West Coast satellite image. I might have put them in the wrong order. Let's see. Yeah, here it is, sorry. So here's the West Coast satellite image over the last several hours. And here you can see the open cellular convection coming in from the Gulf of Alaska after the main cloud band that comes through with the first kind of weak cyclone. And we saw both components of the reflectivity there just a minute ago. You could see the more well-developed, well-organized portion that comes in with the better, more coherent cloud mass in the front end, and then comes the open cellular convection associated with the cold air aloft on the backside of the upper trough. Most of the Pacific, and this is Hawaii, most of the eastern Pacific into the central Pacific is clear. In the upper levels, and a little bit of low-level stratus cloud, you can see in the light gray. And not a lot of convective elements across going all the way to about the date line, with a big gap, particularly right around 140 or 150 degrees west. And then one gets the impression that there's a strong flow right about in this location, south of the Aleutian Islands, that is anticyclonically curved, and we'll see some evidence for that when we go to our upper level charts. Okay, where was I? Here, I think. Let's take a look at some current weather maps first. And this is the 12Z 500 millibar analysis from this morning. And so here's an upper trough that came through us during the day yesterday. And it was the passage of this feature that gave us that little sprinkle of rain last night around 9 o'clock. And it's now this same entity that's producing the light precipitation over New England. This is several hours old. So over New York and New England, and you're seeing that in the current radar. Broadly speaking, and I'll show you a series of 500 millibar maps in just a minute from last week. Broadly speaking, we've had zonal flow across much of the country all week long, with a couple of exceptions. And that zonal flow, westerly flow across the high terrain, tends to make us a little warmer than Climo, especially during the cold season. And we certainly were early in the week, and we still are even today. It's warmer than it should be, maybe, by the time the afternoon wears on. Just off the coast, you can see a pretty zonal flow all the way from about the date line to the coast of Oregon and Washington. And embedded within it are local regions of intense baroclinicity. This one here is 15 degrees of contrast over a fairly small distance. And so that's part of what we saw with that main cloud head coming in the Pacific Northwest. It's right at the front edge of this region of curvature and strong thermal wind. So this big region of PVA by the thermal wind over the Pacific Northwest. And then the temperatures aloft get really cold. This is the minus 30 isotherm at 500. It's plus 10 on the ocean surface, approximately, and you're at 5 kilometers, so you go to an 8-degree lapse rate. And if the air is saturated, that might be forced to rise. It's freely convective because it's moist. It's a moist adiabatic, or it's an 8-degree lapse rate, and the moist adiabatic rate's about 6. So you're warmer by 2 degrees for every kilometer that you can rise in such air. So it's easy to have strong updrafts, and then just as easy for saturated downdrafts to sink down and create the space around individual convective elements. So that's why you see what you see on the satellite. Minus 36 off the former Queen Charlotte Islands. That's the real cold spot. So the spacing between the cells is likely to be bigger the colder it is aloft because the stability is lower, and the updrafts can be more intense, and the downdrafts have to be more widespread because you got to conserve mass. So it's a kind of an interesting structure across the continental U.S. Bookended upper troughs that are fairly locally, they have local maxima in curvature, nothing really downstream or upstream of either one of them in terms of curvature in the flow. And relatively cold, but not freezing cold, except off the coast of British Columbia. Now I wanted to take a look at the 300 millibar map at the same time. And here it is, and one gets the sense that this jet here, this zonal jet off the Pacific, is quite strong, 170 knots, I think, at its core. 192 actually is what's analyzed. It's not actually supported by an observation, but 192 knots is really strong, and it's right off the coast of British Columbia where you're in this pretty intense jet exit region, and it's also got some cyclonic curvature. So that's a spot where one might expect substantial column stretching and maybe some development going on there, and that was about the pivot point for the front edge of the cloud band that came in too. So that makes all good physical sense. This jet down over the southern plain states has a maximum of about 149 knots. It actually says 150 at Monette, Missouri, so that's a little bit off. But that's probably a subtropical jet, and one way to determine whether or not that's right, we'll go to a higher level and see if it's more intense. And then this feature here is about 144 knots just over maritime Canada and racing towards, there's the southern tip of Greenland racing towards Iceland. And that's also more or less zonally oriented if you take account of the projection difference. So let's, before we go to the lower troposphere, let's go to 200 as opposed to 300 and see what is true about these jet features. Well, first, the one off the west coast was at 192 knots. It's lower at 200. That's a polar jet. This one was only 140 or so at 300. It's 162 at 200 millibars. So that's a subtropical jet. And remember, we saw that little wispy cloud streak across this region of the country. So that's consistent with the presence of the subtropical jet in the same location. And then this feature is almost as intense at both levels. So it may be almost a vertical superposition of a polar and subtropical jet. It's at least probably got a deeper jet core than either of the other two. And then the flow is broadly a giant trough that spans the entire continental United States with flow poleward and from the, well, actually it's east-west. It's pretty much just a zonal flow across the entire, this portion of the Western Hemisphere with a little bit of intrusion in the southwestern U.S. from the tropics. So pretty interesting, but not the most interesting flow I've ever seen. Greg?
John, the one off the East Coast is 8.
What'd you say?
That's 8 on the East Coast there, that jet.
Oh, right here. Yeah, of course it is. Yeah, that's right. Because we just saw with the satellite the incredible outflow coming out of the seemingly renewed convection off the Cape Hatteras flow. And so, yeah, that's been deforming the tropopause and folding it over and producing
the one
a
to the
wind speed
south,
mass.
I don't know where that's from, but it's a subtropical jet for sure.
Yeah, this one here is maybe not got a tropical, the same kind of tropical origin. This one definitely owes some of its intensity to the tropical storm. Yeah, for reasons we'll talk about in 751, 452. Okay, let's go to the lower troposphere for a minute at the same time before I show you some of the movies that are of interest. Today's 850 map, which is right here, is kind of less interesting than any of the other ones that'll show in the animation. The Pacific Northwest starts to show some thermal structure there because you're finally over the ocean, but the Intermountain West is always a mess, and the strong baroclinicity is hard to detect anywhere on this map. That was not quite the case yesterday, and it certainly wasn't the case on Tuesday and Wednesday. This is maybe a little sliver of the baroclinicity that kind of came through us last night, and it's now weakened and moved to the east. But it was enough to drop the temperature from the low 50s to the high 20s in a short amount of time. And the dew point's considerably lower today than it was. But it's not a well put together flow, I'd say. There's no single obvious cyclone center in the eastern half of the United States. There's Ada. There's a little bit of that storm in southeastern Ontario, but it's not got a very obvious frontal structure. It's poorly put together. And then the stuff off the Pacific Northwest, all really one sees is pretty cold air, even at 850 millibars. This is 0 degrees, and that's -5. So that's pretty cold in the same place where it was even colder, of course, at 500. Broad northwesterly flow and cold advection occurring over the eastern Pacific. Okay. Let me show you a couple other things. Let's see. Is this the animation? No. No. Yeah, this is. Okay. So first I want to zoom in a little so you can see it better. Okay. This is the 500 millibar map from last Friday, 0Z. Okay. So here's the setup for we're already into, I think we already are into our first day of over 70 on Thursday. So this is the second one. And you can see a broad zonal flow across the higher latitudes of the Canadian and U.S. Rockies. That helps to produce a warm bubble in the immediate lee. And that was part of the story for us in terms of staying warm. This giant ridge that was kind of sitting over the southern plains and putting an anticyclonic flow over us at about this, well, a week ago last night, was also part of the setup. So there's a broad, fat ridge over the eastern 2/3, maybe 3/4 of the United States, and a very intense upper trough that's just off the coast of Oregon and California. And notice this intense horizontal baroclinic zone. These lines, the red lines are isotherms every 5 degrees. It's -31 in the middle of this thing. So that's a pretty intense upper front. And so one wants to watch what happens with that as we go forward. So that trough digs to the south, becomes a bit of a cutoff trough, almost cutoff, I should say, and then it takes on a broad, positively tilted orientation that gets us through about, what was this, Monday, 12Z. So this was the last 70-degree day, and I should have asked you to pay attention as we watch those several panels go by, but the flow remains strong and from the southwest over the central plains and up into the western Great Lakes states the whole time. Here's the upper baroclinicity that was first pretty intense around that upper trough off the Pacific Northwest. That's the upper baroclinic zone, and it's kind of broadly deepening that upper trough and putting it in a positively tilted orientation. So we stay in southwesterly flow. I'll just go back. If you take a look at southern Wisconsin, the whole time the flow is either westerly from high latitude Rockies or southwesterly, and that stays the case all the way through that period of time. And then we keep on going, and we stay southwesterly right through the day on Tuesday. It wasn't very cold on Tuesday, but then look at this little troughlette that develops right here over western Kansas, eastern Colorado, southern Nebraska. And that's a locally intense baroclinic zone as well. So this region of curvature is coincident with a pretty intense thermal wind, and we start to have substantial PVA by the thermal wind down shear of it, and that's going to lead to, as the wave progresses across us, this is now Wednesday night. Is that Wednesday? I get my days wrong. This is Tuesday night, I guess, right? Yeah, Tuesday night. That's when we started to have a break in our weather, of course. We had a more substantial, we had rain on Tuesday, and then we had some other interesting things going on across the region, which I think I want to show you from, where's my perspective? Here it is. From Tropical Tidbits. It's easy to call up the old solutions to the model. That's why I want to show you this. Let's see if I can zoom in. Maybe I can't. Yeah, a little bit. Okay. So this is that same time, 0Z on Wednesday. We have a cyclone immediately down shear of the upper trough, about 995. Here's the precipitation that came through, intermittently convective and heavy, and sometimes not so heavy around us. Here's Ada at that time, middle of the week, and you can see that It doesn't take much imagination to suggest that any sort of flow that's tied to Eta and any sort of flood of tropical air is going to easily be entrained into this southwesterly flow all the way through Tuesday, and that kept our dew points high. But look at this, snowing in Minnesota, northwestern Iowa, and then the eastern Dakotas. And so we saw this in class the other day. There was when the radar was a really thin line of mostly intense convection, and then this sort of bulbous region of what looked like lighter precipitation on the radar, but it's just because it was snow. So one really sees these structures start to emerge at this time of year. We have linear precipitation bands along the fronts, and then more isotropic looking disturbances in the precipitation field to the north and west. And they're controlled by different dynamics. That's why that's true. And so let me show you a cross-section through this forecasted precipitation band. And I'm trying to cut it so I'm about perpendicular to the thickness lines. I like to make the line fairly long too, so I get a nice aspect ratio. And this will be the frontogenesis in theta E. And I think it also shows some omega. Yeah, so there's our theta E is in green. And here's the tropics, 330 degree Kelvin theta E in November 10th. Where is it? Down here over Indiana in Illinois. I mean, that's unbelievable, unusually high. And then notice the stratification. These theta E isotropes are just about vertical. So there's little or no resistance to moving in the vertical direction. And then right in this spot, in the lowest couple of hundred millibars, one gets a fairly intense low-level frontogenetic forcing. And so that's going to help to produce a thermally direct circulation. And in the region of poor stratification, you get a pretty nice updraft. Actually, I'll take another one in a different spot. And it's quite sensitive across this region. Some of them are just plumes that go straight up to 100 millibars, 300 millibars. But this one you can see is an updraft and a downdraft, kind of in the vicinity of that frontogenetic maximum. Let me get you one more cross-section through this thing. Maybe a little further north. Let's see what this one looks like. Yeah, there's the one that I'd seen earlier, something like this. Now the forcing is not much different. It's still a sort of a stubby little lowest 200 millibar frontogenesis maximum. Look at the theta E. It's absolutely vertical. This is the 320 degree Kelvin moist isotrope, 325. It's absolutely vertical. You give a little bit of an impetus to air that's saturated, it must be saturated, and you get this extraordinary updraft that goes all the way to 300 millibars. And that was probably one of the narrow, intense convective lines that came through and rained heavily on us a couple of times during the day. But it's forced by low-level frontogenetic action, and then it has the right thermodynamic environment to go crazy. Greg?
You ought to take a cross-section through the tropical cyclone up across the front where you see the fold. I'm thinking, if you think of a four-cell pattern around a jet max, you have a direct circulation on the entrance side. And I think the tropical cyclone's the upward motion in the direct circulation on the entrance. And then the other cyclone is the upward motion on the exit region on the other side.
Okay,
so
I think
both these tropical cyclones are working together on this frontogenesis process.
I think I know what you mean. I don't know how we would get that captured in a cross-section unless you took like latitudinal averages of vertical motion and cut across them.
One from the tropical cyclone to the northwest.
Like this?
Yeah.
Okay, let's try that.
Into the trough.
So let's go from there all the way up to like that. How's that?
Yeah, go down a little further south, up there. Yeah, about there, yeah.
Okay. So let's see what we get there. So it's a little bit confusing. B is close to the tropical. B is on the north side. This is the tropical cyclone side.
Okay.
So that's what it looks like. And so we're seeing the frontogenesis along the cold front right here, and the plume of ascent, plume of descent. And then the tropical cyclone, this is ascending air as well. And the core of the tropical cyclone's just barely off the map. We couldn't get it. We couldn't get right through the middle of it on this cross
section. We may not
section.
be in the outflow there, but would the outflow be going from left to right across the upper?
Yeah, so I think I know what you mean. You say if you just imagine a structure in here that's kind of a conduit between these two things. Here's ascending air, and then presumably descent and descent. And that does give you the impression it's got the same type of circulation as what you get around the jet.
Well, sometimes I see the outflow go right into the entrance region of the jet,
The northern jet.
the northern.
Yeah,
jet.
yeah, yeah, okay.
So that's what I'm wondering if we could find out. But I think we got to use some other graphics to do it.
Perhaps so,
This is
yeah.
gonna show it.
But I think there's no question, you said that last Friday, that these things are operating in some sort of cooperation. I think that's correct. I don't have any question about that. Though I did last week. I was thinking it was a different storm. Okay. So I think that's what I wanted to show you about the past week's weather. Pretty sure that's it. I don't know if I've got anything else on this sequence. No, I just had other levels. So what I'd like to do next is go to the forecast into the weekend, and then maybe a little bit beyond the weekend, and show you some things from that. So with some trepidation, I'll get rid of this web page because I don't expect to visit it again, and I'll put this one off to the side. So let's first go to our department web page, and I don't think I'm using the newest ones, but that's okay. Let's just jump ahead to tonight. 0Z on Saturday, and we've got this giant anticyclone sitting over the central United States, and we're kind of enjoying the weather associated with that right now. And remember, we had mentioned there's a really intense zonally oriented jet off the Pacific Northwest coast in the northern part of the Pacific Basin, and little disturbances are developing along. And here's one right here that's going to get itself together, and it doesn't exist quite now. So this is in 12 hours in the forecast. There it is. This might be the front edge of that cloudiness we saw on the satellite that's just moved inland today, and later on in the day it moves even further inland and covers the whole state of Idaho. And then there'll be convective elements in the cold air, and they show up as this sort of aggregate of lightest precipitation between 0.01 and 0.05. But they can be really interesting and impactful. I like to pay a little more attention on this scale to these types of disturbances. There's no such thing going on in the central U.S., and there's Eta racing along the baroclinic zone toward Iceland, but still locally dropping, an inch or more of precipitation every 3 hours. So it's a very intense little disturbance. And then a broadly unsettled Caribbean, and we saw a couple of things in there on the satellite that might be of interest later on. So I want to see if there's any relationship between these features that was that 12 hours out? I think it was. Yeah. Here's the 500 millibar map at the same time. And so here's disturbance number one, this little front edge of this little vorticity feature south of the Aleutian Islands. I think that's the one that's connected with that first disturbance that we saw in the Northeast Pacific Ocean. And then here's the front edge of another sort of linear vortex strip. Perhaps it has upper frontal characteristics, but only weak ones, coming into Northern California. And that's about all I'm going to point out on this map. And then there's broad zonal flow. That doesn't look very different from the current time. And at 850 millibars at this time, some of the consequence of the broad zonal flow shows up nicely here in the central plains. This is the beginnings of a lee side trough. So you can see the geopotential height minimum in the white lines is coincident with the low level, or the 850 millibar temperature maximum. Very characteristic of lee side pressure troughs. Here's disturbance number one south of the Aleutians. Got a broad thermal wave to it, but there is a local vorticity maxima that seems tied to the front edge of that 500 millibar feature we just saw. And then broad warm advection over the northern plains and western Great Lakes states. So we should have pretty nice, maybe slightly moderating temperatures over the next couple of days if this persists. And it should persist with the persistence of the zonal flow across the high terrain. So let's take a look at what happens in the next 12 hours after this. I guess we'll go to 500 first. This time, so this is valid tomorrow morning. And there's the front edge of the upper vortex structure. Now it's moved into the southern Gulf of Alaska, so we'll be watching something developing in there. There's a little bit of troughiness developing just to our west over the intermountain states, and that's not well organized yet. A couple of different local vorticity spots are obvious in that, but a broad upper trough, and so generally speaking, places in the central plains to our west will be downstream of the upper trough axis by the time tomorrow morning arrives. And then the East Coast, this is probably the signature of Eta, the 22.1 times F, and as you can see, it's still heading straight poleward. And let's go to 850. So at 850, our disturbance off the Pacific Northwest has moved to, a position that absolutely ties it to the upper disturbance we saw at 500 millibars, starting to look like a nice warm frontal zone here and a cold frontal zone to the west. So that's a nicely formed structure. It might be interesting to see on the satellite tomorrow. The lee side trough structure has become a little bit more pronounced. Again, a function of the broad westerly flow over the high terrain, particularly warm over Kansas, the pan mills of Texas and Oklahoma. And that does continue a broad warm advection over us. I think the temperature has gone up on the order of 6 or 8 degrees in these 12 hours at 850, and that's likely to be communicated to the ground. So we'll have definitely a moderating day during the day tomorrow by temperature standards. And there's Eta going off the coast of maritime Canada. And quickly, just a peek at the sea level pressure forecast. There's our disturbance in the Pacific Northwest. It's got a little precipitation maximum, which is interesting, but it's right the same disturbance we've been looking at there. And then broad warm advection across us in the central plains, and then pretty intense cold advection over New England, and there goes Eta off to a rendezvous with Icelanders. So let's go ahead to 36 hours. I don't know why I did that. Okay, let's get a better picture of that. 36 hours. So this is now 0Z Sunday, and this is getting close to the time where I want to bring in Biz 5D. But first, look at this upper vortex, how it's kind of really nicely congealed just off the coast of British Columbia. So down sheer of this, one might expect there's been substantial lower tropospheric development. And look at how this has all been put together. We started out just 12 hours prior to this with a collection of sort of not so well organized vortex features at 500 millibars. Now it starts to look like something. It looks like a deep upper trough, and it even has a linear sort of backbone here that we're going to interrogate at 060 in just a minute. And that starts to spawn a pretty intense cyclone is going to develop in our vicinity during the day, late in the day, Saturday into Sunday. So it's going to get windy here on Sunday. And those are the two features of interest that I think I'd like to focus on. So at 850, we're at 36 hours, right? Yeah. So you can see that this disturbance in the Gulf of Alaska region has really intensified. These are geopotential height lines every 30 meters. And so suddenly we have a closed disturbance and we have 5 closed contours in just this 12 hours. So there's been a period of quite intense development for this central minimum in geopotential height. And notice that we've got a broad upper trough over the central U.S. at 850. But notice how even before there's a clear central cyclone sea level pressure or geopotential height minimum, the baroclinicity is getting well organized. This is a really intense baroclinic zone stretching from really the Mississippi on the Iowa-Wisconsin border down to northern Oklahoma. So that's going to bring some sensible weather changes to places in the plains overnight on Saturday. And this whole complex is going to get a little bit better organized. You might already notice right over Lake Winnipeg is a minimum in geopotential, but then there's a secondary minimum over southeastern Minnesota. That's the one that really starts to get picked up by the presence of that upper vortex at 500 that was right about here. So that's going to really start to develop right over us and to our west. And so I want to go to 6 hours, just 6 hours ahead in the forecast. Here's 500 millibars. So this is midnight tomorrow night. This upper vortex has gotten much more intense. It's now got values over 3 times the Coriolis parameter, and prior to that, it was in the range of about 2 times the Coriolis parameter. So how does this 500 millibar vorticity get strong so fast? It must be advected downward from somewhere else. So this high vorticity must be coming from somewhere else. I'm alerted to the rapidity of that development. Makes me think we've got an upper front in this vicinity. No matter how the vorticity gets here, once it's here, it's liable to be differentially advected in the vertical, and that is a really good developmental mechanism. So we'll watch out for that. Look at this thing taking its time now, making landfall in British Columbia. It's a pretty intense circular upper vortex off the west coast of Canada. At 8:50 at this time, things are looking different. That's a really intense cyclone. We'll see in a minute what the sea level pressure is, but quite intense. And then here's the separation of a separate geopotential height minimum at 06E midnight tomorrow from the broader one to the north. And this one is now involved in this lengthy cold frontal baroclinic zone that goes all the way through the Central Plains, and that's the one that's going to develop. And at sea level, you can see a couple of things. This precipitation might be underdone, but that's okay. 986 millibar low, just over sort of Green Bay or Lake Winnebago. That's going to mean pretty high winds for us overnight Saturday, because this is an intensifying disturbance. The pressure is falling in the middle, and we're going to get the winds to rev up. Look at this little thing off the coast of British Columbia, 973. That's like a little hurricane in terms of its size and in a really rapid development. So that's going to be something to contend with on the coast of British Columbia. And they have big fir trees there, so it could be bad news. And we're going to see later in the week, and I'll just mention it briefly, when we get to the end, there's going to be potential for a big windstorm in the Pacific Northwest later on in this period, maybe Tuesday, if I remember right. But this is the thing of great interest. 986, look at the strong cold advection that's flooding the central Mississippi Valley, and we'll soon be involved in that ourselves. Sunday will be cooler, and I think we'll see some snow in the air on Sunday morning. But now, having gotten this far and watching this evolution, the thing that was of interest to me for our own weather was the amalgamation of what was a poorly organized set of little vortices in a broad upper trough into something that's much more intense. You can see it, the intensity of the upper baroclinic zone reflected in the thickness field. Something really intense develops there. So I want to show a few things about that feature in Viz 5D. So let's see if we can't do that. And I'm going to stop at this time, that is 06Z on Sunday. So this is the sea level pressure map for that time from the GFS. And you can see there's the double-barreled cyclone center, the one that's, I think, not going to be the predominant storm to the east of Lake Winnipeg, and then the one right over Wisconsin. And so these are every 4 millibars, and that's a pretty intense pressure gradient force. And there's the cyclone off the coast of British Columbia. Now, let's take a look also at 500 millibar, approximately 500 millibar theta. And that's going to be, oh, come on, don't be doing this to me now. I wonder if it just doesn't like sitting around all this time, Pete.
I think it's because you stretched the screen.
Oh, is that right?
See how it's vibrating there? If you just start it up again,
okay.
make the screen big to begin with.
Okay, it seems to have picked that up, okay. Yeah, there's theta, so I don't know why that happened. Let me just put the 500 millibar theta on top here. And these are every 3 degrees Kelvin. And so you can see kind of a broad but not well organized baroclinic zone, same here. But what's going on here over Kansas and Missouri? That's a really sharp upper baroclinic zone. That's every 3 degrees, so how many? 1, 2, 3, 4, 5, 6. That's like 15 degrees Kelvin over a really small distance. So, and its relationship to the sea level pressure is that immediately in the thermal wind direction, immediately down shear of this maximum and horizontal temperature contrast is where we have our development going on. That's curious. We might want to see if there's any particular connection there. And one way to assess that is to look at the upper vorticity. So this is the 500 millibar vorticity. I can zoom in on that spot. So that's 500 millibar vorticity in green. Sorry for the clutter on the map. And then one can imagine the thermal wind is parallel to these isotherms. Here's the last 2 contours of the maximum in the vorticity. So I have really intense thermal wind advection, positive advection of vorticity by the thermal wind into this region of the map, and that's where the development's going on. Okay, and if one looked at this through the whole deep column, one has a better perspective on the whole process. But the development is being driven by PVA, by the thermal wind, is what I can conclude in a quick glance from this map. But let's do some more. Let's instead take a cross-section through that upper front and look at theta in a vertical cross-section. So I'm going to go right through the heart of it, and notice I'm drawing it perpendicular to the isotropes so that I get the best look at the structure of this thing. And that is, let's see. That is a pretty intense upper level front. So these are every 3 degrees. I'll zoom in a minute. But this bundle of isotropes represents the upper front. A few of them, not in that bundle, but another bundle of isotropes create a surface front. So this is a very deep tropospheric baroclinic zone. The main upper front goes from about 312 perhaps to 300 Kelvin. So this bundle right here. And it stops maybe around 700. Lower stratosphere has an obvious front as well. Okay. Let me show you some other things about this cross-section. First, I'll zoom in to the point of interest. That's the upper front. And then let's take a look at the wind speed. How about the wind speed in this cross-section? These will be every 10 meters per second, starting at 30. So 30, 40, 50, 60, 70. So there's a 70 meter per second jet core right about there, and that's at a height, I'm sorry I can't show you what it is, but it's about 9 kilometers. And then really strong vertical and horizontal shear, and that's coincident with the region of strongest baroclinicity because it's frontal. You've got to have both of those things. And then notice that the horizontal shear is a lot weaker on the anticyclonic shear side. There's reasons for that. And then what if I put the vertical motion in this cross-section, just the subsident vertical motion, and that's right here. So these are all, this is air that's sinking at least 2.5 centimeters per second, and then every 2.5 in from that. So it's, some of these places are going down 15, 20 centimeters per second. Here's the jet core again, and the subsidence is right through the jet core on the warm side of the baroclinic zone. This is forcing upper level frontogenesis, just as we've been talking about in class. And one of the other consequences of that process, and we'll come back to another piece of it in a minute, is that you're going to also have a tendency to pull the tropopause down and pull, therefore, high potential vorticity values down along this bundle of isotropes. This red level was approximately 500 millibars, 5.4 kilometers. So the upper tropospheric, lower stratospheric PV comes down to about 700 millibars in this upper frontal region at this time. And the jet core, again, was right there. So this subsidence is forcing that PV downward, and it intercepts the 500 millibar surface as a vortex structure. Watch this. I'll put the vorticity back on, and as I tilt up, see that? That's right where the PV is hitting that red surface. That's where I have my maximum vorticity at 500 millibars. So that's where this vorticity comes from. And I want to show one last thing on this. Let's get rid of the vorticity. We'll put pressure on top. I think that's further up. And zoom in. So this is the pressure. Remember, this is a height coordinate model. So I'm showing pressure in green, or light green, and the isotherms at the same level in the red. And this was the cross-section line we had, right? And this is a region of geostrophic cold advection. And that's forcing the strong subsidence onto the warm side of the baroclinic zone that's producing this upper front. And that's dragging the high potential vorticity down from the lower stratosphere into the middle troposphere, which then converts itself to large vorticity, and you've already got the thermal wind because you've got a strong baroclinic zone, and the PVA by the thermal wind is going to bring tree branches down around here on Saturday night. So that's what's happening to produce this weather event that we're about to experience. So that's pretty cool that you can see all of this really plucking a weather map at random today, because this is just the way things go in November, and we got a beautiful example of it on our doorstep. So one last thing, I just want to show you what goes on, if there's no questions, that is. I just want to show you what goes on for the rest of the week. I think there's a nice development that goes off the California coast, but I don't exactly remember when that occurs. So let's jump to 60 hours. I think it's going to be evolving out of this really minuscule weak disturbance of 1,012 millibars. This thing turns into a monster storm in the Pacific Northwest in a short order. And look at how intense our storm is. So this is just now Sunday night. We're down to 977 in southeast Ontario. Howling winds, even stronger in Michigan, especially the UP. But it's going to be a windy Sunday for us. And getting colder as that wind comes in. So let's go a little bit ahead and watch that thing in the Pacific Ocean. So that was 60 hours. Let's go to 72. That's down to 1,000. Okay, it's looking like a little bit better organized weather system. It's got a warm front stretching out over to Oregon, maybe something resembling a cold front back on the side. But it's a sort of an odd football-shaped minimum in sea level pressure. That's at 3 days. Let's see, at 78. Oh, rats. I know, Pete, you have a better product, and I've neglected to use it, but just I'll see if I can get something that looks better. No. Just give me a second. I want to get the stuff that really looks good.
You got to go to the Weather Watch page.
Yeah, that's right. So, and we'll be looking at 81 hours because we're 78. We were just at 72.
Keep going. That's the, there you
Right,
go.
yeah. Okay. So we were just at 72. Let's look at 78. All right, so I don't know what the number is in there, but let's see. 9, that's 1,992. It's something like 994, so it's looking a little more intense. But same sort of odd, stretched out shape along the baroclinic zone. And let's go at higher frequency now. That's 72, was it? No, 78, so we'll go to 84, sorry. 84 hours. Oh, wait a minute, now this thing's starting to get more intense. We're at 1,004, 1,996, 992, 988, 984. So that's a lot of development. And it's occurring right off the Pacific Northwest coast. And that was 84 hours. Let's go to 90. Wow. It's down to, I got to count them again, 1,000. 1, 2, 3, 4, 5, 6. That's 24, 976. So there's a lot going on this development, and it's going to be windy along the Pacific Northwest coast. Very windy. Even, look at that. Look at how intense and small scale the center of this disturbance is at this time. This is down to, that's 980, 76, 72, 68, 64, 962. Where did this thing come from? Okay, it's really intense, and it's howling. If you're at the mouth of the Columbia, the Dalles here in Oregon, you've got extraordinary offshore flow into the center of that thing. That's a windy place to begin with, but that's going to be a really windy early part of the week for them. We'll go one more time to 102 hours. It's even worse. I mean, this is like a mini hurricane right off the southwest of the coast of British Columbia. This is down now well into the high 960s, maybe even lower than that. So it's really going to howl in the Strait of Juan de Fuca on the early part of the week. You will not want to be out on a ship. And let's take a look at the 500 millibar map at this time, which is 102 hours, just to get a sense of where this might be coming from. And there's a pretty intense little vortex embedded within this broad upper trough, but that's the main little vortex that's really developed over a period of time, and it's come from down off the California coast in an oblong shape into something that's much more wrapped up. So it's a very interesting development, and I don't want to, since I haven't looked at it in any more detail than this, I don't want to say any more about it right now. But it's a very interesting development. So there's always something going on when you get to mid-November and then further along. One last thing I want to show you. I can't neglect to do this. And that is, it's been a few weeks since I gave you the update on our cold pool. Where are we? Well, it's fairly interesting where we are. I'm going to exit this. Yeah, please, just do what I ask, would you? And then, where is that folder? Rats. Oh yeah, here it is. So let's take a look at this. So this is our current cold pool for the minus 5 degree and colder air at 850 beginning September 1. And this is November 12th, so it's through the 12th of November. So the average is, there's 3 different averages, but the long-term average is in blue. And we were most of the season below average till late October, and we had a little bit of above average, and now we're back to below. this doesn't strike me, at least by eye, as a particularly warm year, but it turns out to be the 8th warmest year through November 12th in the 72-year time series that I have from the NSEP reanalysis. So it's so far, the Northern Hemisphere autumn has been really warm. It's in the 88th percentile or something for warm autumns. And I have no idea, of course, what that portends for the winter, but the winter begins, for me, in this measure, on the 1st of December. So we've started winters with cold pool areas in the below 50 million square kilometers, almost below 50 square million kilometers. And so we're headed in the right direction, of course. It's hard to resist climatology, but we're doing it. 13 of the warmest, let's see, is this right? Yeah, the top 13 warmest falls up to this point have all been since 2003. And that doesn't mean every year since 2003's made it, but it means almost every year has. So we are definitely out of hoaxville. This isn't a hoax. This is just weird that it's happening year after year after year that we're warmer than the long-term average. It's just global warming, and it shows up in this signal, or in this time series, really well. Whether you're in the winter, heart of the winter, or in the lead up to the winter, they both show the same thing. So that's all I have for today. Are there any comments or questions?
Can we take a look at the Wisconsin climate? I'm curious what that last 5 days of 70s looks like. Ed said he updated it for us this morning.
Oh yeah, so where would I go for that state climatologist?
AOS weather page.
Hey, come on, what's going on?
There you
Okay.
Go to our weather page.
Okay. Okay, weather.
And then on the left bar, Madison climate data, third from the bottom.
Oh yeah, okay.
There you go. Wow.
Oh wow, look at that. That's our 5 days over 70. Actually, it's our several days over 68, but
Looks like
that
we've got
just...
we have lows that are more
Wow.
higher than a normal high.
Yeah, look at that. Isn't that amazing? That's the high dew point from the tropical cyclone. Yeah. 3 days in a row with dew points that were well above 50, obviously. Unbelievable. And in fact, if you don't get that, those are the 3 days that make it an exceptionally long streak. The first two happen every once in a while, but they're not the last three, and you got to have those high dew points to make it happen. Really interesting. I think that's a cool story. So that is a, talk about a sore thumb. That's a sore thumb. That stands out.
Wow.
Pretty awesome.
Looks, you know, there could be a correlation with tropical cyclone season, because this was the most tropical cyclones in a season recorded already.
Yeah.
And you have a very warm fall. Maybe the warm periods over the fall correlate well with extended periods of tropical cyclone activity.
Could be, because what you're fighting on my analysis is the southward encroachment of the -5 isotherm. And if you're consistently being battered by tropical cyclones, you can push back on that, push it back to the pole, and that's going to show up as a warm fall. That's right, by that measure. That's a good point. I wonder if there isn't one. I never thought of that. That's a really good thing to check. Maybe especially storms that come from September 1st on, the number from that period of time or something. Yeah. What an interesting problem. Okay, any other comments or questions? All right, Pete, thank you so much for taping, and thanks everybody for your attention and questions. This was a good discussion. We'll have another one next Friday. Then we'll do everything else subsequently online, it looks like.
Yeah, the week of Thanksgiving we won't have weather.
No
watch, and
discussion.
then after that it'll be online.
And then we'll do the others remaining online. So, and that might mean Michael Morgan can join us.
Yeah.
Which would be good.
All right.
All right, thanks.